In this presentation, you will be learning about renewable energy sources. We will focus on wind energy and solar energy. And then another day, you will be looking at non-renewable energy sources. Solar and wind have great potential, but from this presentation, you should learn some of the benefits and some of the risks, some of the drawbacks to these renewable energy sources. Pay close attention to the graphs and data tables provided, and carefully watch the videos to gather all the information you can, because at the end of this unit, you will be assessing what we should be using for energy sources in order to keep the warming to 1.5 degrees Celsius. This is what scientists tell us we must do to avoid the worst impacts of climate change. So think about our future and which renewable and non-renewable energy sources we should be choosing. And of course, this is science, so you're going to want to have evidence to back up your claim.
We've all seen those creaky old windmills on farms, and although they may seem about as low-tech as you can get, those old windmills are the predecessors for new modern wind turbines that generate electricity. The same wind that used to pump water for cattle is now turning giant wind turbines to power cities and homes. Okay, have a look at this wind farm in the California desert. A hot desert next to tall mountains, an ideal place for a lot of wind. Here's another one on the windy prairies of Wyoming. Now, today's wind turbines are much more complicated machines than the old prairie windmills, but the principle is the same. Both capture the wind's energy. Okay, here's how it works. First, a wind turbine blade works sort of like an airplane wing. Blowing air passes around both sides of the blade. The shape of the blade causes the air pressure to be uneven, higher on one side of the blade and lower on the other. And that's what makes it spin. The uneven pressure causes the blades to spin around the center of the turbine. On the top, there's a weather vane that's connected to a computer to keep the turbine turned into the wind so it captures the most energy. Now, the blades are attached to a shaft, which only turns about 18 revolutions a minute. And that's not nearly fast enough to generate electricity by itself. So, the rotor shaft spins a series of gears that increase the rotation up to about 1,800 revolutions per minute. And at that speed, the generator can begin to produce electricity. So, why are wind turbines so tall? Well, the higher up you go, the windier it is. More wind naturally means more electricity. Larger turbines can also capture wind energy more efficiently. The blades can sweep a circle in the sky with a diameter longer than a football field. Now, what's really cool is that even a small wind farm like this one in Wyoming can generate enough electricity to power more than 9,000 homes. And larger farms can provide much more clean energy for our homes and businesses. And it's not just on land that turbines can capture the wind. Our oceans and the Great Lakes provide a reliable and consistent source of wind that we can capture and turn into electricity. The Energy Department is supporting innovative offshore wind projects that will help build some of the first offshore wind turbines in U.S. waters. As the wind energy industry continues to grow, offshore development has the potential to significantly boost domestic renewable energy production, especially in coastal areas. With more than 50% of the U.S. population living within 50 miles of a coastline, capturing wind off America's shores has the potential to provide energy to countless homes and businesses. Wind energy, on land or offshore, a reliable and renewable clean energy source, helping move America toward energy independence.
This visual shows a comparison of renewable energy sources in yellow on the left side to non-renewable energy resources in gray on the right side. The units are terawatts. A terawatt is 1 trillion watts. And we can see that our energy consumption each year, the whole world is using 16 terawatts. So looking at this visual, you can make some conclusions about which resources we can use, which ones will we run out of, which ones can we never run out of. Compare solar to tidal and wind, which will provide the most energy. Take a look at our coal and uranium and natural gas and oil resources. Remember, these are non-renewable, meaning this is all that we have left. So what you're going to do now is answer the questions on your study guide. All the answers are in this visual, and that should help you gather some data about what sources of energy we should be using globally moving forward.
So this graph is looking at the prices, the average price of these different energies over time. We can see the time is down there on the bottom. We got 2009 all the way to 2019, so this is our most recent part of the graph. And we also have the dollar amount going on the up and down axes. So we want to, in number 8, record down the most recent cost for each one of these energies. And you can see the energy lines are color-coded with the name of the energy there, so you can use that as you record it. And then number 9, we want to say the 2 cheapest. So looking at this pie chart, we have 2 pieces of information: jobs for fossil fuels and jobs for non-fossil fuels. So the green is looking at non-fossil fuels overall, all the different possibilities of non-fossil fuels. So we see that number in the pie chart there, 542,000. And then on the right-hand side, it specifies of all those non-fossil fuel energies, if you just look at wind and solar, that would be 353,000 for just wind and solar. Okay, and then same thing for fossil fuels. We're looking at the pie chart black, all the fossil fuel jobs, 211,000, right? But then when we look at just coal within the fossil fuels umbrella, we see that's a little lower there at the 86,000. So use those numbers to answer your questions.
This graph shows where on Earth there is greater or less potential to use solar power as an energy source. This is based on how many hours of adequate solar radiation they receive. And the scale goes from very poor solar potential, being the purple to the left here, to the redder colors, yellow and then red. Deeper red means much greater solar potential.
So this diagram on the left is showing annual average wind speed. We can see here the different colors. So the best or highest wind speed is this dark purple and then red area across the Midwest. The yellows and the greens, those are the lower consistent wind speeds. This side over here, we're looking at states that have generated the most wind electricity. So this is in billion kilowatt hours. So the really dark green, one state is over 30 kilowatt hours. And then the other dark greens are the highs, 20 to 30 and 10 to 20. So the darker the green, the more wind electricity they've generated.
So this is our example of a wind turbine. We have our wind supply here and then our turbine, which is producing electricity. And we can actually see that since we have a generator inside, we are producing actual electricity right here that we could convert to your house or to a battery or to a bunch of different things. So we can see evidence of how that actually produces electricity right on this lap quest here.
Is a solar cell, also called PV cell, that has a semiconductor in it that is able to take the energy from the sunlight coming through the window and also from overhead and convert that, excite some electrons and get electricity to flow through the wires here. My multimeter is measuring 2 volts approximately of electricity flowing through here. And if I move my solar panel up to be getting more light, my volts go up to 2.2. So on a much larger scale, of course, this could be used on the roof of my house to power my home.